Case Study: Revolutionizing Cybersecurity Defense. TechSecure's journey to adaptive threat mitigation using reinforcement learning. Amid increasing cyber threats, TechSecure, a leading cybersecurity firm, has recognized the potential of reinforcement learning to enhance its defensive mechanisms. At the heart of the firm's innovation team are Dr. Emily Chen, an AI specialist, and Jake Harris, a seasoned cybersecurity analyst. Together, they aim to transform TechSecure's static, rule-based systems into dynamic, adaptive solutions capable of responding to ever-evolving threats. TechSecure's traditional intrusion detection system had limitations. Static rules and signature-based detection methods struggled to keep up with sophisticated attacks. Emily and Jake faced the challenge of developing an IDS using reinforcement learning, focusing on Q-learning, a model-free RL algorithm. The goal was to enable the IDS to dynamically adjust detection thresholds and adaptively deploy countermeasures based on real-time interactions with the network environment. The Q-learning algorithm leverages a Q function to estimate the expected utility of actions taken in specific states, updating the Q values iteratively using the Bellman equation. The team aimed to optimize the agent's policy to maximize cumulative rewards, balancing immediate gains against long-term benefits. How does the Q-learning update rule contribute to achieving this balance? The update rule considers the immediate reward and the discounted future rewards, ensuring that the agent learns from both short-term and long-term consequences. Integrating deep reinforcement learning into their IDS design, the team used deep neural networks to approximate the Q function. This approach was particularly advantageous given the high-dimensional state and action spaces in cybersecurity. The DRL-based IDS needed to identify patterns of malicious traffic, adaptively mitigate attacks, and minimize the impact on legitimate traffic. What specific benefits do deep neural networks provide in the context of DRL for cybersecurity? They offer the ability to handle complex, high-dimensional data and generalize learning across diverse scenarios. The team decided to test their DRL-based IDS against distributed denial-of-service attacks. These attacks aim to overwhelm a target system with excessive traffic, rendering it unavailable to legitimate users. Traditional mitigation strategies like rate limiting or IP blacklisting were insufficient due to the evolving nature of such attacks. The DRL-based IDS needed to learn from real-time network traffic, identifying and responding to malicious patterns effectively. During the initial phase, the system had to balance exploration and exploitation. Excessive exploration could trigger unnecessary alerts or disrupt normal operations, while excessive exploitation might result in suboptimal performance. How should the IDS balance exploration and exploitation in such dynamic environments? The agent could employ strategies like epsilon greedy, where it mostly exploits known high-reward actions, but occasionally explores new actions to discover potentially better strategies. One challenge the team faced was the sparsity and delayed nature of rewards in the cybersecurity setting. Unlike gaming environments, where rewards are frequent and immediate, the outcomes of deploying a particular defense strategy might not be immediately observable. How can delayed and sparse rewards be managed in RL? Techniques such as reward shaping and temporal difference learning can be used. Reward shaping involves providing intermediate rewards to guide the learning process, while temporal difference learning handles delayed rewards by updating estimates based on future reward predictions. As the DRL-based IDS began to adapt, it demonstrated improved detection and mitigation capabilities. However, another critical application area emerged: automated malware analysis and classification. Traditionally, static analysis tools struggled to keep up with evolving malware techniques. The team envisioned using RL to dynamically analyze and classify malware based on behavioral patterns observed in a controlled environment. In a sandbox environment, an RL agent could execute malware samples, monitor their actions, and classify them based on the observed behavior. This approach aimed to detect previously unseen malware variants and adapt to new attack strategies. How does sandboxing enhance malware analysis using RL? Sandboxing provides a controlled environment where malware can be executed without risking the actual system, allowing the RL agent to safely explore and learn from the malware's behavior. Network defense posed another significant challenge for TechSecure. In a typical enterprise network, defenders must continuously monitor and protect numerous devices and communication channels. RL offered the potential to automate and optimize defensive measures, such as deploying firewall rules dynamically in response to detected threats. This involved balancing security and usability, ensuring that defensive actions did not overly restrict legitimate activities. The network defense RL agent needed to continuously interact with the network environment, learning to adapt to changing threat landscapes. How can RL agents adapt their strategies in dynamic network environments? By continuously updating their policies based on real-time interactions and feedback from the environment, RL agents can improve their decision-making capabilities over time. Despite the promising results, the exploration-exploitation dilemma remained a persistent challenge. Excessive exploration in a real-world cybersecurity context could lead to unintended consequences, such as triggering alerts or disrupting normal operations. Conversely, excessive exploitation might prevent the discovery of more effective strategies. How can cybersecurity systems balance exploration and exploitation to maximize effectiveness? Incorporating techniques like adaptive epsilon greedy or using a decaying exploration rate can help balance exploration and exploitation dynamically. The TechSecure team also explored the potential of reward shaping to address the sparsity and delayed nature of rewards in cybersecurity. By providing intermediate rewards for achieving specific milestones, the RL agent could be guided more effectively through the learning process. How does reward shaping influence the learning trajectory of an RL agent? Reward shaping helps the agent by providing additional feedback, making the learning process more efficient and effective. Through continuous testing and refinement, the DRL-based systems at TechSecure demonstrated significant improvements in intrusion detection, malware analysis, and network defense. The adaptive nature of RL allowed these systems to evolve with the threat landscape, offering robust and resilient cybersecurity solutions. In analyzing their journey, Emily and Jake recognized the importance of balancing exploration and exploitation, managing sparse and delayed rewards, and leveraging deep learning techniques for complex scenarios. The integration of RL into cybersecurity strategies proved to be a powerful approach, providing systems capable of learning from interactions and adapting to ever-changing environments. For instance, in addressing the exploration-exploitation dilemma, the team found that adaptive exploration rates, which reduce exploration as the agent gains confidence, were particularly effective. This strategy allowed the IDS to discover new attack patterns without compromising the stability of the network. Additionally, reward shaping was crucial in guiding the learning process, especially in scenarios where immediate rewards were scarce. In conclusion, the implementation of RL in TechSecure's cybersecurity framework transformed their approach to threat detection and mitigation. The ability to learn from real-time interactions and adapt to dynamic environments enabled their systems to become more resilient and effective against advanced threats. As RL algorithms and techniques continue to evolve, their application in cybersecurity will likely expand, offering new opportunities for enhancing cyber defense.